In this lecture, we are going to study other kinds of locks other than spin locks and study their key ideas. So in this video, we are specifically interested in two lock implementations, which is one is ticket locks and the other is CLH lock. And I will briefly explain the key idea of those two. The first idea for mutual exclusion is by using release-acquire synchronization as in spin lock. Recall that in spin lock we are using release-acquire synchronization via the message on the lock location to ensure that you are having mutual exclusion. Once you acquire a lock, you always have a latest view on the data, and you are always releasing the latest view on the data when you are releasing the lock. So that is achieved by the release acquire synchronization from an unlock function and to the next acquire function of the lock. So yeah, the view synchronization or view transfer is performed from the end of the critical section to the beginning of the another. And here, in the implementation, a single location is used to do that in the spin lock. And this key idea is also used in other kinds of locks, for example, in ticket locks and CLH lock and so on. And furthermore, the second idea is guaranteeing fairness by ordering and waiting with different locations. So let me explain this with a particular example of ticket lock. But let's say that spin lock is missing fairness, which is one of the most important criteria for a lock implementation, which means that if multiple threads are trying to acquire a lock at the same time, it may be possible that a single thread is repeatedly acquiring the lock without giving any chance for the other threads to acquire the lock at all. And this is a bad behavior of a lock, but spin lock doesn't exclude such a bad behavior. On the other hand, ticket lock is guaranteeing the fairness by, as I said, ordering and waiting with different locations. So I will explain this idea in the implementation of the spin locks. So now I'd like to first look at the ticket lock implementation here. So ticket lock has two locations, the current and the next, and both of them are atomic word. So they are actually containing the number. And at the beginning, both current and next are 0. They are both 0 at the beginning of the execution. So far so good. And when you acquire a lock, then you are executing fetch and add, which is atomically increasing the value of next here, and you are getting the old value of the next. So basically, the ticket means that the order of the critical section, order of the lock that is performed by multiple threads. So if your ticket is 0, then you are the first to execute the lock. If your ticket is 1, then you're second. If the ticket is 2, then you're the next. Ticket is 3, you're the next. And now the critical sections are ordered by this ticket. So you are issuing a ticket as in the bank. And you are trying to load the current value. And if it is different from the ticket, you are just breaking out. And if it is the same, it means that it's your turn. if current is 0 and suppose that you incremented the next by fetching that here and you get 0, and now the next has just become 1, and you know that you are the first to execute this lock because the current is 0. Here you acquire the current and it must be 0 at the beginning. And it is same with the ticket, so you are breaking out this loop and return the ticket. Oh, I am having a turn to execute the lock, and I am, for example, the first or the second to execute this lock. So, and this ticket number is returned. And later, when you finish accessing the underlying data, you are trying to unlock it, and you are given the ticket you are given from the lock function. And now what you're doing here is, oh, I'm done with this underlying data, and it's the next thread's turn to execute this thread. So now we increment the current by storing ticket plus 1. So this is basically a plus 1, but the arithmetic is wrapping around. When you add from the maximum number of the word, then you are getting 0. So it is wrapping around from the maximum value to 0. And here you have to do a release here because it must be synchronizing with this acquire for the next thread. So let's look at the implementation a little bit more. So recall that in the spin lock there are only one locations. So the one location is indicating whether the thread the log is acquired or not. And the location is used to synchronize two consecutive critical sections. On the other hand, in this implementation, this current value and the next value are existing. There are two locations. And the current variable is used to synchronize the two consecutive critical sections. So in the previous critical sections unlock function, you are storing a value by release, as we did for the spin lock. And for the next critical section's current unlock function, it is reading the current value with an acquire. So there must be a release acquire synchronization, and as a result, the latest view on the data that is protected by the log is released by the previous critical section's unlock function, and this view is latest, and it is acquired by the next critical section's lock function. So as a result, inside the critical sections, the threads must see the latest value in every critical section. So that's guaranteed by this release acquire synchronization. Okay, so far so good. And furthermore, this next variable is used to order multiple threads, multiple critical sections. So it is different from, so the order is decided well before this current release acquire synchronization happens. So the order and this synchronization is done with different locations. That's already discussed in the slide where I said that ordering and waiting are done with different locations. So ordering is distinguished by this current variable, and waiting is on this next variable. They are different. So the reason why it can guarantee fairness is that the fetch and add, this operation is fair in the underlying architecture. So when multiple threads are fetch and adding at the same time, then it is guaranteed that the multiple threads are getting at least a number. So it may be possible that a thread is getting lower values always, but it is possible, it must be the case that if multiple, for example, 3 threads are trying to fetch an ad at the same time, then they are anyhow succeeding in the operation. So they get, for example, 0, 1, 2 consecutively. So if a function, a thread is calling a lock, then it at least get the ticket. And when it just waits for the ticket turn to arrive, then it will eventually, it is guaranteed that it will eventually get a turn and return from this lock function. So that is guaranteed because this order is decided with a separate location, and fetchNet is used for ordering the multiple threads. And fetchNet is fair. That's the reason why this entire ticket lock implementation is fair. Okay, so far so good. That is the implementation of the first lock we'd like to discuss, which is ticket lock. So I will summarize the key ideas once again in the end of this video. And let's turn to the next implementation of the locks, which is the CLH lock. So CLH is the acronym of people names. The last names are, one of the people's last name is C, and the other's last name is L, and the other's last name is H, and they collectively wrote a paper on this lock, and this lock is a famous lock for many reasons, and I will explain the internal working of this lock. And the CLH lock is basically linked list, and linked list is, in the linked list there's an order among the nodes, right? And each node represents the critical section. For each critical section, a new node is created, and this new node is waited for. So this is the implementation of the CLH lock, and let me tell you a little bit more about this. Okay, and at the beginning of a CLH lock, so you are creating a node, a new linked list, and the linked list is actually containing a single node. For each node in the linked list, it contains only a single boolean, which is atomic boolean here. So node is atomic boolean. But unlike the conventional linked list, it is just containing a single value, boolean value here. But the link is somehow implicitly stored in the token for each critical section. So I'll explain this a little bit more in the explanation. So at the beginning of a CLH log, it is creating a node, a pointer to the node basically, and this pointer to node is has this type, immutable pointer or constant pointer to the node, which is cache padded. So here, for the reasoning purposes, this cache padded doesn't play any interesting role. So let's say that it's just a constant pointer to node, and you are creating a new node here. You are allocating a new node inside a heap, and the underlying value is false. Locked is false, at the beginning. And this false value is allocated in the heap, and its pointer is stored in this node. So for these two functions, please consult the Rust standard library documentation. It is basically converting a smart pointer, this box smart pointer, into a row pointer. That is actually a word. So at the beginning, you are creating a false node and then return the node. And as defined here, the CLH log is containing a single node, pointer to the single node, which is meant to be the tail pointer. Okay, let's see what's going on here. So at the beginning, you are creating a box. And at the beginning of the execution, you are having a node like here. And at the beginning, the log contains the single node that contains the false box here. So this is the beginning of the lifetime of a log. It first contains a pointer to the false box allocated in the heap. Okay, so far so good. And now you want to implement the lock and unlock function here. So what's going on here let's see what's going on in the lock function. So here you are creating a new box here. So that new box is has the value true, and this box is allocated in the heap, right? And now you are trying to swap the tail pointer, and you are trying to swap the tail pointer. The tail pointer becomes this node, and the old value of the tail is assigned here, pref. So it is also an read, modify, write instruction. It is atomically swapping the original value of tail and the new value of node here. It is done atomically. So you get the pref pointer. So what's going on? Let's see what's going on in this diagram. So you are creating you are basically creating a new node, and you are atomically replacing this. So in this diagram, this becomes this is what was node here in the code, and the first block is now in the pref variable. So essentially you created a new node that contains the true value here, and also you are atomically replace the lock with the new node here. So you get the pref block, which is the one before the original tail before lock function, and this new node created in the lock function is now the new tail. It is pointed by the lock. So let's say this is tail. So this is the figure right after doing this swap. Okay, so far so good. And now we are reading the value inside the proof. So we are reading this. And we are repeatedly reading this value until this becomes false, basically. If it is true, it is looping again. If it is false, then it is breaking out. And as a result, then if the control flows to this line, then it's guaranteed that, oh, this proof becomes false. So far, so good. And now we are destructing or deallocating the pref box here. So now this is just deallocated. This is by this drop function. It is restoring the box and it is dropping the box, which automatically deallocate the underlying location in the heap. Now the token is returned. The token is the pointer to the new node. So the node here is returned as a token. So that is basically what's going on here. So now the first is deallocated and this node becomes a new tail and it becomes true. And this true means that the critical section is now currently holding the lock. It is this pointer is currently locked by the critical section that just has created this node. And so far so good. And now let's assume that another function, another thread is trying to acquire the new node here. So let's say that this node has the name A, and now this A is the prev of the next lock function here. So A was here, and if another thread is calling this lock function again, then this prev becomes the old tail, which is the A. So if A was in the tail right after the previous thread's lock function, inside the next thread lock function, A becomes the prev. So this is the same node here. And now in the code, it is waiting for the prev prev value becomes false, but it is true. So now it is trying to wait. It is repeatedly checking if this becomes false, and it is waiting for this becomes false. So it is locked. So it is very much expected because we need to provide mutual exclusion. If the previous lock function is not concluded with the matching unlock function, the next lock function should wait, and it is waiting on this location. And now, if the previous lock function is concluded with the unlock function by the same thread, for example, the same thread will call the unlock function with a token, and the token is the node here. And in the unlock function implementation, the value is stored with a false, and in this case with a release ordering. So what happens in this figure is that, and let's say that this is accompanied by, this is lock 1, and this is, let's say that this is unlock 1. If the lock 1 is the concluded and it is calling the unlock function, then it is storing this to false. and it is released, right? And yeah, this is basically what's done by the unlock function. It is storing the false value to the token, which is the node here. So this becomes false by the unlock one's execution. And now the second stress lock function is able to break the loop here because it becomes false, and it is acquire reading the value here. So it knows that, oh, this becomes false, then I'm breaking the loop, and now lock 2 is deallocating the block as we did in the lock 1 function, and then return this function. And it is now lock 2's turn, the second thread to turns to execute the code and access the underlying data. And now let's see why mutual exclusion is guaranteed. So mutual exclusion is guaranteed by the release acquire synchronization on this location. This becomes from true to false, and in that time, the first thread unlock 1 function is releasing its latest view on the data, and lock 2 in turn is acquiring the view and now acknowledges the latest knowledge on the value. That is done by this variable here in the new node here. Okay, that is the motivation, and that is the internal working of these locks. And now, if lock 2 function is finished, then it is now pointing to a new node, which can be waited for by the other lock functions as well. Okay, and this is basically the implementation of the CLH lock. And now let's return to the slide here, and let's read this slide again. So the implementation is in this slide, and the implementation has 2 characteristics or key ideas. Again, always mutual exclusion is guaranteed by release acquire synchronization. In spin lock, in ticket lock, and CLH lock, the same. Some location is released and acquired by consecutive critical sections. And the location is the single location in the spin lock, and the curve variable in the ticket lock. And for CLH lock and the MCS lock, we will learn later, the ordering location is a new location for each new critical section or each new waiter. And critical section is created, a critical section creates a new location, and that location is waited for. So this is basically what's going on here. So that is the key idea. And ticket lock and CLH lock provides fairness. How? They are separating the role of the waiting and ordering into 2 locations, or more than 2 locations. So in ticket lock, the orderings are decided by the current variable, and waiting is done on the next variable. And for current variable, the ordering is decided by the fetch and add, which is a fair instruction. Similarly, in CLH lock, the ordering is decided on the tail pointer and by the swap instruction. Swap is also fair instruction because it just replaces the old value with the new one, and regardless of whether stress is fast or slow, it is guaranteed that it is eventually succeeding to execute the swap instruction. In that sense, it is a fair. And this fair instructions guarantees the overall fairness of the lock operations. And that is basically the key idea of guaranteeing fairness, ordering and waiting with different locations, and having using the fair instructions for ordering the critical sections. And here, ticket lock is ordering with next and waiting with current locations. And CLH lock is ordering with tail location and waiting on a new location for each critical section. Okay, so far so good. But what is not particularly desirable for CLH lock is that in CLH lock, a new node is created by a previous critical section, and that is deallocated by a new critical section. So each node is allocated and deallocated by different threads, and that is undesirable for performance. And let's see the implementation here. In the implementation of CLH log, the box is created here, and allocation happens in the lock function. And this node is now transferred to the next lock function by this tail operation. And inside this tail operation, inside this log operation of the next critical section, the same node is dropped here. So it is the evidence that this node is created, allocated, and deallocated in different threads. And this discrepancy is very detrimental to performance, because now the allocation and deallocation is a multi-threaded job, and usually it will degrade the performance critically. If allocation deallocation happens in the same thread and they are well optimized, because there is no interaction of the other threads, but in this case there is an interaction of multiple threads, then that degrades the performance quite significantly. And now, in the next video, we are going to learn the MCS log, which resolve this problem. So the allocation and deallocation happens in the same thread in the MCS log, and as a result, they may have a higher performance, better performance, basically. Okay, this will be dealt with in the next video. So this is basically what's discussed in the next video. We're going to study MCS and MCS parking logs, and they are trying to overcome the performance degradation of the CLH log. Okay, so there's a homework. This is not a formal homework you need to turn in, but I strongly recommend you to draw an execution in the promising semantics for each log. So we already studied the implementations, right? The implementation of the ticket logs and implementations of the CLH log. And I assume that you are not particularly well versed at these logs. You just saw the implementations. So you need to understand these logs by actually drawing the figures of the promising semantics and the executions in the promising semantics of those logs. For example, please draw the figure for ticket log with 3 locations. For example, for the ticket log, you have to draw the memory for 3 locations: the current and the next and the data. So this is from a log, and next is also from log, but data is the data. And I want you to draw the similar figure as we did for spin log in the slides. And furthermore, for CLH log, the situation is a little bit more different, complicated. And you have data, and you have the the location for the initial node, and the first critical sections node, and the second critical sections node, and on and on and on. And I want you to draw the promise semantics figure for these multiple locations for CLH lock and the ticking lock. And you can freely share your drawing in the GitHub issue tracker so that I can give you some feedback. But please try to draw the figure on your own and see if it is correct or not, and ask if correct or not in the GitHub issue tracker. Okay, so far so good. And in this video, we studied the two implementations of the locks. The one is ticking lock, and the other is CLH lock, and they have two key ideas here. So please look at these two key ideas, and it is very important for the overall lock implementations. So this is the two key ideas of the lock implementations. And ticking lock and CLH lock is trying to overcome the previous locks on limitations. So spin lock is not fair. So ticking lock is introduced to guarantee fairness by ticket queuing. So the next variable is used to ticket queuing. Log order is decided by a fair instruction. But the limitations or the cons of this ticking lock is that it has a slightly complicated API because the lock function returns the ticket. In the spin lock implementation, the lock function doesn't return anything because it doesn't need to. But in the ticking lock, it should return the ticket because in the unlock implementation, the ticket is used to advance the current variable to the next one. So there's trade-off. It is fair, but it has a slightly more complicated API. And for CLH lock, it is trying to improve the scalability by using per critical section spinning location or waiting location. So in the spin lock implementation and ticking lock implementation, all the threads are waiting for the single location. All right. In the spin lock, the single location is waited for. All the threads, all the waiters are trying to see if the location becomes false. And in the ticking lock, all the threads are trying to read the single location, which is the current, and see if the current matches with its own ticket. So the single location is read and written by multiple threads, and it is usually detrimental to the performance because there is actually a sharing, and this actual sharing has a negative effect on the cache coherence protocol, and it will incur the cache coherence traffics and cost basically. On the other hand, in the CLH lock, only one thread is waiting for a single location. A node is weighted by a critical section. So it is very much helpful for performance because no two threads are contending on the single location. And as a result, it is a linked list of spinning location, and this per critical section spinning location is greatly improving the scalability. But the limitation is that it has a space overhead because you need to create a new node for each critical section, and that may be detrimental to the performance. So you have to use wisely. You have to choose wisely among multiple lock implementations depending on the situations. And in the next video, we are going to study the MCS and MCS parking locks, and they also improve upon the previous log implementations for specific purposes. But they are all having trade-offs. No single implementation is outperforming in every aspect. So you have to study the characteristics of these logs, and we will continue to discuss the trade-offs of multiple logs in the next video.